Welcome to Archimedes and Science. In today's video, we will be discussing the density of brown versus white eggs. And we want to find out which type of eggs is more dense. So we all know that eggs sink in water. Why? Well, that's because the density of eggs are usually larger than water. So objects that have a larger density than water, they sink in water, and if they have a lower density than water, they usually float in water. So what is density? Density is defined as the mass per unit volume of a substance. In other words, we can obtain an object's density by dividing its mass by its volume. So usually, the symbol for density is called rho. It's a Greek letter, and the mass is denoted as m, and the volume is denoted as V. So if we do m divided by V, we get density. And the standard unit for density is 1 kilogram per meter cubic. This is a rather small unit, meaning that in a cube of about 1 meter in each side, the mass of the substance contained is 1 kilogram. That's a very small actually number. Usually the density of air is about 1 kilogram per meter cubic, and most other substances have a density much larger than 1 kilogram per meter cubic. So the other unit that is commonly used is called 1 gram per centimeter cubic, which is equal to 1,000 kilogram per meter cubic. So another common concept that is usually used is called specific gravity, or SG. That is defined as the ratio of the density of a substance to that of fresh water. So take the density of the substance rho, divide by rho of W, which is the density of water, we get the specific gravity, which does not have any unit, as the units of the two densities cancel out. So what are the common values of density? We all know that fresh water has a density of exactly 1 gram per centimeter cubic, or 1,000 kilogram per meter cubic. And 1,000 kilogram is also a ton. So in other words, in a cube of 1 meter in each side, the mass of the water contained is exactly 1 ton, or 1,000 kilogram. And then we have a lot of these metals, like gold. They are a lot more dense. And such, for example, gold is one of the most dense materials on Earth. So the density of gold is 19.6 grams per centimeter cubic, or 19.6 times heavier than water. Or in kilogram per meter cubic, it's 19,600 kilogram per meter cubic. And we also have other substances that has a lower density than water, like ice. So ice has a density of 0.917 gram per centimeter cubic, or 917 kilogram per meter cubic. That's why ice float on water. So how do we actually measure the density of a substance? Well, we need to know the mass, and then we also need to know its volume. For the mass, we can easily measure it on a scale. When we put an object like an egg on a scale, we are actually measuring the weight. The weight of egg is equal to the mass of egg times the gravity constant G. So the G constant here is 9.8, and the G number is 9.8 per meter per second squared. And from this, we can actually get the mass, which is just equal to the weight divided by the G constant. And that's usually actually displaced on the scale. This measurement is very precise. Even for scale that used for kitchen use, one can get a precise measure of about 0.1 grams as its uncertainty. So for an egg, which usually has a mass of about 50 grams, that's equivalent to 0.2% uncertainty. To measure its volume, well, the egg doesn't have a regular shape. It's kind of oval, but we cannot really get the exactly oval shape. So you cannot use the geometry to determine its volume. On the other hand, we may actually just place the egg in water and then measure the volume by looking at the change of the water level. Well, it's a very straightforward method. Unfortunately, the measurement won't be that precise. because all the graduate cylinders, the best we can do is roughly 5 mil in terms of uncertainty. So that's 5 centimeter cubic, or for egg, it's about 10% error. That's huge. So that's not precise measurement. So what else we can do in order to get a really good measurement of its volume of an egg? What we can actually use the buoyancy force. The buoyancy force is actually depending, it's related to the volume of the object. So let's see how this can be done. If we take a beaker of water and weigh it on a scale, we are measuring the weight of the beaker plus the weight of the water. Next, if we actually take an egg, attach a string, and then just gonna suspend it in water. And now what are we measuring? It's actually, you will see an increase in weight. But actually, the increase in weight is not equal to the weight of the egg. Instead, it's actually equal to the buoyancy force experienced by the egg. Why is that? Because as the egg is suspended in water, it's experiencing upward buoyancy force from the water. So this upward buoyancy force is exactly to the volume of the egg. Now, according to Newton's third law, this upward buoyancy force is from the water acting on the egg. But then the egg is going to also give opposite force, or called the reaction force, to the water, which is not downward. That's where you actually get this increase in weight. So it's actually the downward force exerted by the egg onto the water. And that force is, in magnitude, is the same as the buoyancy force. So we get the W2, which is the weight. Now we have is the weight of the beaker plus the weight of water plus the buoyancy force. So if we look at the difference of the two, it's exactly equal to just the buoyancy force Fb. So take the difference of the two weights, and it's equal to the buoyancy force according to Archimedes principle. That's equal to the density of the liquid times the gravity constant G times the volume of the object. From this, we can now solve for the volume of the object by dividing by the density of water and the G constant. And this is what we have here. Because the density of water is exactly 1 gram per centimeter cubic, so the value of W2 minus W1 over G gives us the X volume in centimeter cubic. And therefore, the density of egg is mass divided by volume. The mass is equal to W0 over G, and the volume is equal to the W2 minus W1 over G. So the G and G cancel out, and we obtain the density of the egg as W0 over W2 minus W1. And that number is not in units of grams per centimeter cubic. So this is really elegant method. We just need to weigh three things, get the three weights, and then we can compute the density of this egg or any other object using this method. So to kind of illustrate the use of this method, we bought large white eggs and large brown eggs from Trader Joe in January 2023. And here are the specimens we have here. And you know that eggs are actually very expensive, and that you're limited to just can get each household can only get like 2 cartons of eggs, 2 dozens of eggs. So we take brown egg number 6 as an example, and we weigh it, and that's our the mass of the egg itself. And then we weigh a beaker of water for 97.2 grams, and then we suspend the egg in water. And we did this by holding the egg, putting the egg in a holder, and then suspend it, and we get 5.2 grams. So now, because the holder is used, so we have to take that into account in figuring out the volume, because right now it's not just the egg of the volume of the egg, but the volume of the egg plus the volume of the holder is being measured. So here are the numbers. The mass of the egg is 60.1 grams directly measured here. That's our W0. W1 is the weight of the beaker plus the water for 97.2. W2 is the one with the egg. So the difference between W1 and W2 is actually the total volume, the volume of the egg plus the volume of the holder. And since the volume of the holder is 1.9 centimeter cubic, that's already been determined. We can determine that using exactly the same method illustrated here. So the net volume of just the egg is 58 minus 1.9. So that's 56.1 centimeter cubic. So now we have the mass of the egg, and we also have the volume of the egg, and we can do M divided by the V, get the density, which is 1.071 grams per centimeter cubic. Now, because the uncertainty in our measurement is purely due to the uncertainty in the scale here, which we can measure up to a precision of 0.1 grams, and using error propagation, we can also estimate the uncertainty in the density of the egg is equal to 0.003. In other words, the density of brown egg number 6 can be determined to this precision. So it's 1.071 plus minus 0.003 grams per centimeter cubic. That's a pretty accurate measurement. So now we can actually look at other samples. So we did that for all the y-axis, 1 to 6, and the mass varies a little bit, so is the volume. But on average, the mass of the y-axis is 56.083 grams. The average volume is 52.067 centimeter cubic. And for each egg, we do mass over volume. We determine the density of each egg. Also, the density of these eggs vary a little bit from 1.06 to about 1.09. That's kind of the range. On average, the density of this y-axis is 1.077 grams per centimeter cubic. And we did the same measurement for all the brown eggs, and these are the results. You can see the mass also varies a little bit, but on average, the mass of the brown eggs are bigger, larger than the average mass of y-axis. Note that both eggs are called the large eggs. On the sort of the container, it says large y-axis, large brown eggs. So it does seems like there's a little bit difference. So the brown eggs are a little bit heavier than the y-axis. And so the volume are also a little bit larger, but the density for each of the brown eggs, we can compute the density of each brown eggs, and they're very consistent. It's about 1.07, except this egg number 5, which is slightly bigger. The average value of all the density is 1.076. So these two densities are very, very close. In fact, they're just within the measurement uncertainty of our measurement method, because the uncertainty we can estimate is about 0.003. The difference between the two is 0.001. So from this method, basically, we cannot tell if the density of the y-egg or the brown eggs are any different. So in conclusion, the brown eggs are slightly larger in size and also a little bit heavier than the y-eggs. They're both called large eggs, but the mass is slightly different. But to our really kind of surprise, we found these two types of eggs have nearly the same density. Our method cannot tell the difference between two. So they're differ only by 0.001 grams per centimeter cubic. So I hope you have enjoyed this video. And if you like this video, or if you like to see more of these kind of videos, please click the like button and also subscribe to our channel. And thank you for watching.